Okay, so hey you guys, got some good questions, and since I think these are pretty common questions for this unit, I'm just going to go ahead and do a quick video doing them. So someone asked me about number 15 and number 16 on the factoring over R homework. So whenever they ask you guys for zeros in this unit, they're asking for real number zeros. I'm always very clear about that in my directions, and I specify, do I want you to factor over C over R, so just pay attention to that distinction as you're going through the assignments. So for 15 and 16, we're going to go ahead and enter in the real number zeros. Separated by commas, enter the exact value, not decimals. So that means that if there's a square root, they don't want you entering a decimal approximation for that. So how I suggest doing these to start is, if there's anything that's easy that you can do in the start to make the problem simpler, some of those things would be, and I'll list them out even if not all of them are going to be applicable here. Factor out a greatest common factor. So I look at the 1, -3, -3, 1, and I really don't see anything, so not going to be helpful. Then I look and I see, okay, there's 4 terms. Can I maybe factor by grouping? Sometimes there's some that are really easy that way. And when I look at the 2 pieces, I don't really see anything I could factor out to leave me with common factor, so that won't work. And lastly, if you have a quadratic, you could do the quadratic formula to help you and reverse rig the factors as we started practicing last week. But again, we don't have a quadratic here. This is a cubic. So none of those easy things are going to be applicable here, and that's okay. But I just wanted to make sure you guys know that those are tools that are out there. So, okay, if we don't have any of those, pretty much our only option moving forward at this point is let's make a list of all the possible rational zeros that there could be. So the rational roots theorem comes up with a list of possible zeros, but they're not all going to be the zeros. They're just going to be possible zeros. And then we're going to make a, quote, guess. It's not really a guess. We're going to use graphing technology to zone us in on the correct ones to figure out which of these are zeros. So when I look at the rational roots theorem, you list out all the factors of the last over the first. The factors of the last would be 1, and the factors of the first would be 1, and then you add the plus or minus. So all the possible zeros here would be plus or minus 1. Okay, so keeping that in mind, I'm going to go ahead and let's take a look at the actual graph. Okay, so moving us over to Desmos here, I went ahead and graphed our polynomial, and it's going to help us guess between those lists of rational zeros what our actual zeros are. So when I look at the x-intercepts, those are going to be my zeros. It's a synonym. So I notice that I have 3 intercepts, but only one of them is appearing on the list, -1. So what about these other 2? I'm seeing 0.268 and 3.732. Okay, so when the question mentioned finding exact zeros, what's happening with these decimals is because they weren't part of the rational roots list, what it means is that these are irrational zeros. These are non-terminating, non-repeating decimals that are likely coming from square roots. So what that means is we kind of know based on this graphing technology where they're at, but we don't really exactly know their value just based on this graph. So what we're going to write down from this picture is we're going to keep track of the fact that -1 was actually the rational zero. Okay, so coming back to our work, we're going to note that the only zero that we saw was -1. And just for the sake of showing me what you guys were looking at so that when I grade your exams, I know what you were going for, please do give me it doesn't have to be like a really pretty sketch, guys. Just kind of list the fact that when you looked at this picture, when you looked at the graph of our y equals x cubed minus 3x squared minus 3x plus 1 on Desmos, we looked at the fact that -1 was a zero. Okay, so the fact that we have that -1 is a zero, the next part is entirely your preference how you want to do this, but the reason we reviewed division is because when you know one zero but you don't necessarily know the others, the only way to figure out what they are is to factor out the factor that goes with the zero you know. So you can do this either with synthetic or long division. A couple people asked me, do we have to do synthetic? No, you don't. It's my preference to do synthetic because I find it faster, but just realize that long division would work here equally as well. So if I was going to do long division, I would divide the original by x plus 1, but since I'm going to do synthetic, I'm going to do dividing by the 0, -1, and I'm setting up my synthetic. Okay, so for synthetic division, you carry down the 1, and then you start multiplying, carrying, and adding. So negative 3 plus negative 1 is negative 4. Negative 1 times negative 4 is 4. Add that to negative 3, and that gives you 1. Negative 1 times 1 is negative 1, so you get remainder 0. And what we've just concluded is that when we go ahead and divide by x plus 1, we get x plus 1 times, if this was originally x cubed, that means that this is x squared minus 4x plus 1. Okay, so now we have something to actually go with, which means that what we want to do is try to factor that x squared minus 4x plus 1. Let me go ahead and... Okay, so we're going to try and factor this x squared minus 4x plus 1 down. Now this, going back to my list, I don't see a GCF, I don't see factor by grouping, but I do see a quadratic. And so the quadratic formula can help us factor this. So using the quadratic formula to find those zeros, negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a. So my zeros are 4 plus or minus the square root of 16 minus 4, which is 12, all over 2. Okay, so then we're going to simplify that. That breaks up into 4 over 2 plus or minus root 12 over 2, which is equal to 2 plus or minus. We can break the root 12 up into root 4 times root 3, so that's 2 root 3. And you see the 2's reduce, so we're left with 2 plus or minus root 3. Okay, so Alexis asked a really good question, which is, when we're finding all the complex zeros, there's another dimension, because when we look at the graphs, we can see all the real zeros, so it kind of gives us some clues, but complex zeros will not be visually represented on the graph. So it's a great question to go over, how do we find a mix of them? So let's take a look at this example that she asked. We have 9x cubed plus 27x squared minus 79x plus 55. So what I'm going to do for this is, first I'm going to treat it as factoring over r. So I'm going to do the same things that we're kind of used to. First, I would look to see if there's a GCF, and 9, 27, negative 79, 55. I really don't see any. So then I would look and say, like, okay, can I factor by grouping? Again, 79 is a prime number. I just don't see any way to pull anything out here. So not going to do it that way. And it's not a quadratic. So the quadratic formula right now, right away, is not helpful. So the first thing I'll do is I'll list out all the possible rational roots. And then I'm going to compare that to the graph and see if I can spot any of those as actual winners. So the possible rational roots are when you list out the factors of the last over the factors of the first. And the plus or minus versions are possibilities. So the last, 55, has possibilities 1 and 55, not 2. Let's see, and the next would be 5 and 11. Okay, and the first has factors 1, 3, and 9. Okay, so we have quite a few different possibilities here. We have plus or minus 1, plus or minus a third, plus or minus a ninth, plus or minus 5, plus or minus 5 thirds, plus or minus 5 ninths, plus or minus 11, plus or minus 11 thirds, plus or minus 11 ninths, and then the 55s, plus or minus 55, plus or minus 55 over 3, plus or minus 55 over 9. Okay, so this one's kind of tedious. It's a good thing we don't have to actually guess between all of these. So what I'm going to go ahead and do is I'm going to graph this on my own personal device. And having this list is going to help me keep in mind. I can kind of use my calculator to figure out when I see the decimals approximated on the screen, I now have the exact version of any rational numbers. So hopefully we have some of the easier ones, but even if we have some decimals, we have some possibilities to maybe look for. So I'll go ahead and graph this on Desmos. And you guys are welcome to graph on Desmos as well. Okay, if you're going to be taking a lot of these math classes, ooh, this is going to be a zoom out one, I can see. Okay, so I have... Yeah, I just wanted to make sure to zoom out to make sure that 55 was in range, because as we saw with the possible roots, 55 may have been one. but I can tell from this graph that it looks like we're going to only have one real number. So it looks like -5 is going to be our only real number. So based on the graph that we saw, and this is a part of just showing work because I make sure to put in the directions, show your work. I just want to know what screen you're looking at, basically. Like, it's cool with me that you guys are looking at calculators to help you with these, but just let me know what you saw, because if you graph something wrong, I want to know that that was your only mistake, because that's not going to be very much point loss. If you just accidentally graphed the wrong function or something, that's totally minor, and I can see your thought process as long as you draw what you were looking at. So it looks like -5 was our only zero. So that means that none of these other ones are going to be actually zeros because they weren't on the graph. So when I try and figure out the rest of the zeros, I'm not looking for a rational number. I am looking for an imaginary, a complex number, if you will. So I'm going to use synthetic division. That's my preference, but some of you guys have already told me that you really like long division, and I am not going to discourage you from that. Long division is totally okay. So whatever you want to do, whatever makes sense to you. So we got 9. We got 27, -79, 55. We make sure we represent every coefficient on every power of x. So if some were missing, we'd put zeros there. But this one's not missing any. So let's do our synthetic division. So we carry down the 9. We multiply by -5. -45 and 27. Let's see. I think we'd get an 18. But it would be negative. Yes, okay. And then 5 and 18 gives me 50 and 40, so 90. And 90 minus 79 is going to give me an 11. And -5 and 11 is going to give me a -55. Testing my mental arithmetic there. Okay, so that's good. We got a 0 remainder, which is what we were expecting because we know that x plus 5 is a factor. So what we just figured out is that our original polynomial breaks up like this. Okay, now I have something to go off of to find me the imaginaries. So I went ahead and I found the fact that we're looking at this quadratic. And now I have something that I can actually have a chance at factoring because quadratics give me the ability to use the quadratic formula. So what you'll notice with these polynomials is that if you can get your hands on the quadratics pieces that are irreducible over r, that'll be how you find your complex zeros. So using our quadratic formula, we get x values. So these are the not x-intercepts because they're complex numbers, but they are zeros, if you will, complex zeros. You'll get x is equal to -b, so 18 plus or minus the square root of b squared, so 18 squared. Let's do 324. So b squared, 324 minus 4 times a times c. Okay, so 4 times 9 times 11 gives me 396. Okay, so like we were expecting, we get 324, and it's going to be a negative number. Okay, and then that simplifies into -72, but that's all over 2 times a, so 18. So this one reduces into positive 18 plus or minus the square root of -72 all over 18. Okay, and we're going to want to simplify that a little bit. So 18 over 18 plus or minus the root -72. Here's how you would break that down. You'd pull out the root -1 to give you the I. You'd be left with 72, which breaks up into 9. And actually, we can do a little bit more than 9 and 8. Let's see if we can get a bigger perfect square. So what if we did 36 and 2? And try and just simplify it all in one step. Okay, so that's going to break down into, this is I, and then root 36 breaks down to 6, and we have root 2, and all of that is over 18. So when we reduce the fractions, we get 1 plus or minus 6 over 18 reduces to 1 over 3, so this is going to be root 2 over 3i. So if it wants you to list out the zeros, the pattern that it's just looking for is that you list them out with commas, it would appear. So you would go -5, comma 1 plus root 2 over 3i. Be careful about the syntax here, how you type in that square root. Make sure you use parentheses around the 2 so that it doesn't also include the over 3 in the square root. That's a different number. And again, if you guys have any computer entry issues, just take a screenshot of your screen and I can see what you typed and kind of compare that to the answer key and point you in the right direction as to why you maybe have the right numbers, but like for some reason entering in the computer isn't working out. Just take a screenshot of that screen with the error is the most helpful way for asking me those kind of questions. So I hope this was helpful for you.